One reason we went into gravitation today, I was debating between that and the integrations you use to find moment of inertia, is that the Rosetta spacecraft was due to land 3 minutes after class began. I didn't interrupt class to see that, but I just checked. It's been about 2.5 hours since class, almost exactly 2.5 hours since Rosetta was due to land, and it has landed. Rosetta is actually the Rosetta probe, if you want to be correct. Let's just be correct. Rosetta is a satellite that rendezvoused with a comet, and it sent down a probe, and they described this as 7 hours of terror while the scientific community waited to see if it really would land. It did. Apparently everything is well. I don't know, haven't read the article yet, but there's a lot of celebration. This is very neat. It's a first. We get to find out if this all works, and it seems like it's going to. And we get to find out a lot about composition of comets, the universe, how things developed, how the solar system developed. We're going to get a lot of incredible information out of this if everything continues to work. Okay, well, back to the fundamentals of gravitational interactions and orbital mechanics. Here we're just talking right now about circular orbits, and we want to do actually what's going to be an energy calculation, so what we're leading up to. The question we ended with in the last video was, what do the forces look like as we move out? And I asked people to give me their estimates of what the force would be at the 3r distance as opposed to the r distance. What percent of this would we have here? And estimates range from 7% to 30%. The point is that f of 3r should be 1/9 of f of r, and that would be 11.1%. So anything in the 10% area, 10% approximation would be good. And I have a feeling some people actually calculated that, and that's fine. Calculated it when they made the when they drew the vectors, and that's actually very good. But what we have is the force is proportional to 1 over r squared, because the force is big G, big M times little m over r squared. Big G, big M, and little m aren't going to change in this situation. R does, so the proportionality is with the reciprocal square. And since we moved to 3 times the distance, the reciprocal square becomes 1/9 as great. So this is kind of a depiction. This vector is probably even still a little bit big. But kind of a depiction of the way the force falls off. We also did a force versus radius diagram. If the force at this point is represented by this vertical distance, the vertical component of this point, then if we move out to twice this distance, we're going to get 1/4 the force. So let's see, 1/4, 3/4, 1. That's pretty close. You're welcome to measure it with a micrometer if you like. Not going to stand by my estimate, but we move out to 3 times the distance, and we get what we said here, 1/9 of the force. And at 4 times the distance, we would get 1/16. So your force versus distance graph looks like this. Now we want to figure out, as I mentioned before, how much work it takes to get from here to here, or from here to any distant point. And the distant point I want to really get to is how much work it takes to get from here to an infinite distance. Now there's no guarantee that we could get to an infinite distance with a finite amount of work. We have to see how that works out. So let's start to build the integral that we have to do to determine the work done by this varying force as we move away from the planet. Okay, so what do we have? Well, let's assume that we move from a distance r1 to a distance r2. Ignore this r star, that was added later. We just want to know the amount of work done between r1 and r2. And the first thing we want to do, if we want to calculate the work, is we want to approximate the average force exerted over this interval from R1 to R2. Now we're assuming implicitly that this is a fairly small interval, delta R being the distance interval between these 2 points. And of course delta R is equal to R2 minus R1. Okay, what's the approximate average force between R1 and R2? Well, in terms of just the symbols F of R1 and F of R2, now we know that we can calculate the force at R1 and the force at R2. What would the approximate average force be? Well, the approximate average force, and I should have said approximate here, because this is only an approximation to the average force. The average force doesn't really occur at the midpoint. It's not really the average of the initial and final forces because the force versus position graph is not linear. In any case, the approximate average force, though, would be F of R1 plus F of R2, quantity divided by 2. You just average the two forces. If this is a small interval, that's going to be close enough because the force at R1 and the force at R2, if the interval is small, is going to the two forces are not going to differ by much anyway. Now, we can put that into symbols. Big G, big M, little m over R1 squared, big G, big M, little m over R2 squared, divided by 2. And I'm going to say that's approximately equal to big G, big M, little m over R bar squared. Now that's an R bar. When I looked at it just a minute ago, I thought it looked a whole lot like an F. That's how I read it, and I wondered what I'd written there because I thought maybe I'd lost my mind again. Let's put a little more separation between the R and the bar so we can see that more clearly. So I'm going to use R bar for the average of the two distances. And that's not completely accurate. That's why I have an approximate here, but it's a reasonable approximation if this is a small interval. Okay, in that case, well, this expression equals that. Actually, we came over here and we simplified this expression, and then from that simplification, we came up with this. So let's see how we got from here to here, because we had to go this whole route. Again, not the greatest use of board space, but we never know how these things are going to work out because the series of questions I pose to the class is going to, the answers I get are going to largely determine where I go from step to step. Okay, well, anyhow, still bad planning on my part, but this expression can be written as, we can factor out the big G, big M, little m, and the 2 in the denominator to get 1/2 big G, big M, little m. Then that's multiplied by 1 over R1 squared plus 1 over R2 squared. Now we put that over common denominator, and we get R2 squared plus R1 squared divided by R1 squared times R2 squared. And that's quite straightforward. And then, since R1 and R2 don't differ by all that much, I'm going to say that's equal to 2 times the average value of R squared. Okay? And in the denominator, I'm just going to replace R1 squared times R2 squared with R average, R bar, to the 4th power, approximating both R1 and R2 as R bar. That's not, again, completely accurate. These things are not as linear as that, but for small distances, R1 is as much smaller than R bar as R2 is greater than R bar. So this approximation has pretty good validity, and as delta R approaches 0, it's going to approach complete validity, and that gives us this expression. Now, we're going to build this expression into an answer to how much work is done. The one thing I'm going to do here is I'm going to say, okay, we're going to invoke an R star, which could be anywhere between distance R1 and distance R2. At any point between these two, we wouldn't lose much by just using R star instead of R bar. R bar would be more accurate for an actual approximation, but R star is going to be accurate enough when we let the delta R's approach 0.